Okay, cool. So I'm the first one.
Yes,
Okay.
yes, yep. So I can't see um, the screen yet. Or okay, now I can see you. Okay, so ready when you are, Kevin?
Okay. Uh, okay. Yeah. So hi everyone. I'm Kiwen Pen. I'm from Race Lab in NC State University. So today I'll present my paper timeline for defect reduction planning. So first, before talking about defect reduction planning, I would like to briefly introduce defect prediction. So a defect prediction model typically extract metadata, which are in this case static code metrics, to train AI models in order to predict bugs in new files from future releases of a software project. So it's a typical binary classification problem. Defect reduction, on the other hand, is a little bit different. It's a planning problem that is derived from the defect prediction problem. That is to say, after we got the defect prediction model, we ask ourselves, could we further use such information to not only predict bugs, but also generate some kind of guidance to help reduce potential defects? So, for example, if in some way we could know that a code file is being predicted as defective, majorly because one of the code metrics is too high, is extremely high, we then could potentially propose a plan to developers such that we could advise them to decrease this specific code metric using some code refactoring tricks. Therefore, here comes the major question for our paper, that is, how could we generate such a kind of recommendations or plans using what kind of knowledge? So basically, we need two things. First, we need to find out what feature contributes most to a defective prediction. In other words, we would like to find out what are the most important features in each prediction. Um, Secondly, we need to know that among those important features, which of them are actually changeable. So for the first point, if you look at point two, we can use explanation tools to find out important features. In point two, we can see this is a feature importance figure generated by Lime. It's a explanation generation tool that is known for offering local instance-based explanations. This is this means that for each individual prediction, Lime shows out what features are most important in what way. We can see that some of them are positively correlated, some of them are negatively correlated to the prediction probability. So the reason we want instant-based explanation is that even if two code files are both predicted as defective, their reasons of being predicted in that way might be quite different. And so secondly, as we have known what's the important features, we also want to find out what features are changeable. So if you look at point three, there's a previous study on actionable analysis that shows that different code metrics have quite different change frequency across multiple releases. Therefore, in our case, we designed our own actionable analysis process. That is, we collect all changes patterns in previous releases, such as our plans only keeps features that are both important and changeable. So at this point, at point 4, you can see that using Lime, we can find out important features, and using the actionable analysis process, we can filter out the changeable features as well. And the overlap of these two sets would be what Timeline will propose as a final plans. So as shown by the experiment results, our method is much more performs much better than 4 different prior methods, as well as other baselines. So for the 4 details about our experiments, please go to the URL shown above, tiny.cc/timeline. So to summarize, the lesson we learned from this case study is that when we attempt to use AI tools such as Lime in SE tasks, we should better first consider how to customize or modify the tool with some domain knowledge, which is in this case actionable analysis. As seen in this paper, with some simple modifications, we can get much better results. That's all. Thank you.
Well, thank you, Kevin. So yeah, I think without further ado, I will move on to the next presentation, because then we'll have the last 30 minutes for the Q&A session. So
Sure.
our next paper is automatic fault detection for deep learning programs using graph transformations. So Amin, whenever you are ready, please go ahead.
Yeah, let me share my screen. Can you see my screen now?
Yes, we can.
Oh, perfect. So hello again, everyone. Thank you for introduction. My name is Amin Nikanjam. I'm a research associate working at Polytechnic Montreal, and I'm going to present you our paper, as Beata mentioned. This work has been done by me, Hussein Brayek, and Mohammad Mehdi Morawati, and Professor Fulham at Polytechnic Montreal. In this paper, we are going to find faults in deep learning programs. Actually, a deep learning program consists of data, perhaps a deep learning model, and training algorithm. And usually developers used to employ some frameworks like TensorFlow, Keras, or PyTorch to develop their own deep learning program. When you are developing a deep learning program, there might be multiple design choices like architecture and configurations. You need to indicate the type, size, number, and order of the layers. Also, you need to configure optimizers, regularizers, and activation functions. So like any other software, a DL program may contain some bugs or design issues. By bug, we mean something that lead the program to crash or hang. And by design issues, we are talking about something that may lead to poor accuracy or bad performances. Here I describe you an example from a Stack Overflow post. In this program, there are 3 main problems. One of them is a bug, which is indicated by orange color. It is an incompatibility between softmax and the activation function. And second and the third problems are design issues, which may lead to some bad accuracy or line training time. Mainly, they are about decreasing filter count in consecutive convolutional layer, which is a bad practice, and also decreasing the filter spatial size, as indicated by green in the figure. Sorry, we have a problem for typing slides. In this paper, we have proposed Neuralint. Neuralint is a linter for deep learning programs. It is an automated a model-based approach to detect 23 common faults and the poor design practices inside deep learning programs. The main architecture that we target in the current version of Neuralink is convolutional neural network. It is a specific type of feed-forward neural network, which is very popular and common in computer vision and image processing. To do so, we have proposed a meta model for deep learning program, which represent the base, skeleton, and fundamental properties of them, and then a set of model-based rules to detect faults and design issues. Having these two, we need a checking process to verify models of deep learning programs conforming to the meta model and find bugs and design issues. To have the model, we need to inspect the code and extract the model from the code, and then we can check everything inside the model. Here you can see our meta model. Since we have used graph transformations, so our meta model is designed as a typed graph to illustrate the main properties of a deep learning program. So a deep learning program may have three main components here: architecture, data, and learner. Architecture describes the architecture of the network, mainly layers. We start with input layer, then we will have consequently different type of layer. Each layer may have different parameters, including its type, size, everything, and biases and weights after the training. The data may have contain labels in the apparently the data is mainly there because we want to train the architecture on the data. To train the architecture on the data, we need a learner or a training program. So the third component is the training program, which mainly consists from optimizer, the optimizer function, and also loss function to calculate the loss, and then optimize weights to decrease the loss and train the network. So, and about rules. Again, since we are using graph transformation, our rules have been implemented using a graph transformation. Mainly, we are looking for a match or a pattern in the graph to find it and then replace it with something else. So there are three main parts in each rule: left-hand side, negative application function, and right-hand side or RHS. You need to have LHS or left-hand side on the graph. You need to find it, that there should be a match. Then you don't see the NAC. You should not see the NAC as a negative application condition. Then you can replace or add something to the graph in RHS. So LHS is something that you can see currently on the graph, but should be replaced by RHS. This specific rule is describing about a simple rule. You should not have multiple or redundant activation functions. After each dense or convolutional layer, only one activation function is allowed. So multiple activation function is a bug. So how Neuralink works? Actually, we start with the buggy code. In the current version, the buggy code should be in TensorFlow or Cross, but it can be extended indeed to cover other languages because they are in Python and other frameworks like PyTorch. Then a parser starts to inspect the code, mainly relying based on API that represents different part of the network and also training function inside the program. The parser come up with a model of the network as a graph. Then a checking process starts to check rules upon the model and find faults or design issues. At the end, we may get back to the user or the developer by indicating the type of the fault that we have found inside the program or some warnings on the design issues. The developer indeed may fix his program and then get back to the tool to see whether they are fixed or not. For empirical evaluation, first you have...
I mean, just we are above the 5-minute mark.
Sorry.
So yeah, please try to wrap up.
Yeah. At the end, we have successfully evaluated our tool on 34 real-world buggy program. The recall was about 70%, but precision is 100%, so we didn't find any false positive cases. So yeah, that is my presentation. Thank you again. Here are the links to paper and video. Thank you so much.
Oh, thank you. All right. So, okay, now we will move on to the next paper, which is a SEEP paper, counterfactual explanations for models of code, and I'm guessing Jürgen is going to present the paper, right? Please go ahead.
Yes, sure. Thank you. Am I unmuted already? Yes. Cool. All right, so good morning from my side. My name is Jürgen Sito. I'm an assistant professor at TU Vienna in Austria. This is joint work with Ishil Dilek, Vijay Murali, and Satish Chandra. And we're looking at how we can explain machine learning models of source code with counterfactual explanations. And to get us started, let's contextualize this work a little bit. There have been a bunch of machine learning models that have been proposed for code. Two examples on the left side from the literature that can detect security and privacy issues in C and C++ code, or can predict the method name of a method body that has also been stripped from things like variable names, for instance. And at Meta, we have our own set of machine learning models that we apply on source code and specifically on diffs, commits of source code. Here are a few examples, and there are many more, but these are the three that we go into a bit more detail in the paper and in the long presentation to give you a bit of a context as to where these kinds of explanations make sense for us. And when I say explanations, I mean this. Imagine you want to commit a piece of source code into your repository, and some machine learning model, in this case, a performance regression detector, tells you, big red alert, something's wrong with your code. So you may want to ask yourself, why does my machine learning model think that this code will lead to a performance regression? And this problem is obviously exacerbated if it's not just like a 10-line code change, but imagine there are diffs that we're putting into the system that have hundreds of lines of code sometimes. So cue counterfactual explanations. The word counterfactuals, or the concept itself, comes from the causality literature, and it means an alternate world, right? So, or an input in our case, where the prior circumstances are changed to then assess the consequence of that change. So if you were to look at this concrete example from earlier, if you verbalize this counterfactual we're seeing in this illustration here, we would say, if you had called gen simple instead of gen handle, your code would not be classified as causing a regression. So it gives you a pinpointed contrast between original and counterfactual in this case that constitutes an explanation, right? So what this does for you is it demonstrates how the model's prediction would have changed had the circumstances in the program been different, and concretely and pragmatically how we have to modify the program in a certain way to change the prediction. And we achieve that by posing a series of what-if questions to the model. And if you're looking at this from like a input perspective and perturbation perspective, this can be posed as an optimization problem. What kind of tokens in the input do we need to change in order for the model to flip its prediction? Now, I'm not going to go into more detail here. There are a lot of details in the paper, or you can go to the long presentation. But what I do want to do is I want to go through one concrete example to illustrate how this could actually work. So let's imagine a tokenized representation of some program P that goes through a machine learning model. This could be it. Now, in order to generate an explanation for it, let me explain the optimization problem that we're having in a two-phase process. In the first pass, we want to identify one token explanations, meaning that all the explanations that consist of the change of one token in the input that would change the prediction. So in this particular case, if we were to change set exception stack with set message, then the model will tell us that the prediction doesn't hold anymore from the original input. And I want to point something out here, that in order to arrive at robust explanations, what we're doing is we're introducing natural perturbations. We're using pre-trained models, and specifically the masked language modeling feature, where we mask part of the input, and then we ask the pre-trained model to come up with a natural replacement. The reason we do this is if we were to remove parts of the input will be potentially out of distribution. And then the model is not set to have correct behavior. And now, as we have identified some explanations already with one token, we have expansion candidates as to how we can then extend our explanation to multiple tokens. And we order these candidates by score differential, meaning that if we were to perturb one of these tokens, the idea is that we have a proxy to how close we are to the decision boundary. And now in all the further iterations, we continuously sort these remaining tokens and token combinations based on this differential, and add one more token to it to see whether that would constitute a prediction change. So in the case of set exception message, any sort of extension by one token would not lead us to an explanation. So we set it aside and remove it from our candidate pool. However, now we did find a two-token explanation in this case. If we perturb response body to type and add body to ID, we get a two-token explanation. And then we can continue with a loop for certain size of iterations that is a hyperparameter. So in a set of experiments, we wanted to find out how useful these explanations are to actual engineers at Meta. We acknowledge that these classifiers that we're using are not perfect. So we wanted to know whether these explanations help discern true and false positives. And finally, we wanted to see by some ground truth labeling by a team internally, whether the explanations we generate align with human rationale. And in a user study, we saw that in a lot of cases, these explanations were useful. In the paper and in the long presentation, we go into a bit why certain explanations weren't useful. Spoiler alert, explanations with a lot of perturbations were not considered as useful. So sparseness in the perturbations that lead to explanations were preferred. And then in also a lot of cases, the engineers did find the true positives from the false positives. In the true positive case, people in the study built their own mental model as to why they thought the classifier did the thing that it did. And then if the explanation reinforced that mental model, then it helped them discern the true positive. In the false positive case, the participants in our study were helped if the explanation pointed to unreasonable parts of the input. So if they saw that the explanation constitutes something that is completely out of the blue for them, then it was a sign for them, a signal for them that the prediction was actually a false positive. And in most of the cases that we studied, our explanation generation approach came up with human-like attribution more consistently than a baseline. So to sum this all up, if you have a machine learning model that tells you something about your code, you may want to know why. And what we developed here is a counterfactual explanation generation approach that uses natural perturbations in a greedy guess and check manner to generate these explanations for you. This code will be open source soon. I'm currently cleaning up the code. I promise that when ICSI comes around, like in person, that it'll be open source. Please feel free to reach out on Twitter or email, and I'd be happy to answer questions later.
Well, thank you, Jürgen. So we look forward to that, definitely. We will move on to the next presentation, which is from the technical track, variable semantic representation pre-training via contrastive learning. Jeremy, please go ahead.
All right. Thank you, Preetha. My name is Jeremy Lecomis, and I'm a PhD student at Carnegie Mellon University. I'm here to present VARClear, which is our novel framework for representing the semantics of variable names using contrastive learning. So something I've been working on recently are techniques for replacing variable names with more meaningful ones in situations where they cannot be recovered. So one example of this is decompilation. So on the screen is an example of what a decompiler might output, but this is the original code written by the developer. So far, our metric has been, does the suggested variable name exactly match what the developer wrote? This has some shortcomings, though. For example, current is not considered a reasonable replacement for cur here, even though they clearly have the same natural language semantics. So this current and cur example, it seems relatively simple to fix, but considering only abbreviations misses other cases. So for example, length and size would not be considered semantically similar, even though they are. And other metrics such as edit distance don't quite work. For example, min and minimum have a large edit distance, but are similar. So another option is to use natural language processing tools like Word2Vec that assign words to points in an embedding space where related words are closer together. So this seems like a good idea, but it ends up having different shortcomings. So as you can see in this Word2Vec model, the closest point to the word minimum is maximum, which happens to have the exact opposite meaning. So instead of related names, what we would like to do is generate similar names that can be used as direct replacements. For example, min length and minimum length are related and similar, while min length and max length are related, but they're dissimilar. Last year's ICSE had ID Bench, which evaluated how well state-of-the-art machine learning-based methods align with developers' judgments of variable meanings. So one of the benchmarks that they was asking human developers to rate how related two variable names are. And they found that approaches like Word2Vec and FastText are actually quite effective at representing relatedness. However, they found that the similarity scores generated for the pairs of variables completely disagreed with human scores. So we addressed this using contrastive learning, which is a technique that was originally developed for computer vision. For example, we would like to learn that phrase, the minimum score of an accepted ICSE paper is 3, is close to 3 is the minimum score of an accepted ICSE paper, but far from the maximum score of an accepted ICSE paper is 5. And methods like Word2Vec that only consider context, they're just unable to learn this distinction. So contrastive learning is trained with pairs of labeled positive examples. So what it does is it minimizes the distance between these positive pairs, but at the same time, it maximizes the distance to every other point in the embedding space. So what this means is we just need labeled pairs of similar variable names to train a model. For our training data, we automatically generated a data set that we call GitHub Renames. GitHub Renames was created by scraping GitHub for commits that only rename variables without editing other code. So here's one example from our data set. If you'll note, num trees is changed to number of trees, and min data points in leaves is changed to minimum example count per leaf. Each of these is considered a positive example, and the full data set is available on the GitHub repository. Varclear improves on the state of the art. For relatedness, the Spearman's rank correlation score for agreement with humans improves from 0.73 to 0.80. More interestingly, we also improve the similarity scores from 0.35 to 0.53. You can check our paper if you would like to see more results and more details. And I just want to stress that Varclear isn't only useful for decompilation. Scoring the similarity of variable names has applications to many other problems, including suggesting better names during coding, remapping APIs from one language to another, and detecting subtle bugs that might come up from typos. These QR codes, they link to our paper and a GitHub repo if you'd like to try it out. The repository contains all the code we used. It contains the GitHub names dataset, and it contains pre-trained models that could be used without a GPU. Thanks for listening.
Thank you, Jeremy. So we have the next paper towards training reproducible deep learning models. I'm wondering if we have the presenter here on the stage. We have another paper in this session. We can move on to that one if we don't have the presenter for that one. The next paper is learning to reduce false positives in analytic bug detectors. So Anand, I'm guessing you're the presenter for that. So please feel free to go ahead.
Give me one moment to get set up here. And you all can hear me, right?
Yes.
Okay, great. Okay, everyone can see my slides?
Yes.
Cool, all right. So thanks everyone. My name is Anand Karkar. I'm an applied scientist in Microsoft's developer division. Sorry about that. And today I want to give you a brief synopsis of one of our recent works on using machine learning to reduce false positives in analytic bug detectors. So at a very high level, the premise of our work is that we want to detect bugs in source code. And this is something that static analysis tools have become quite effective at over recent years. And today's static analyzers are able to find many different types of bugs across many different programming languages. One analyzer in particular that's quite powerful and has become quite popular is Infer, which is intended specifically for memory bugs. Two of the things that sort of set Infer apart from a lot of the other analyzers is that by design, it's interprocedural because of the way that it performs its logical analysis. And the other is that Infer supports several programming languages out of the box, including, thanks to the InferSharp project, C# now as well. However, static analyzers in general, including Infer, tend to report a lot of false positive warnings. And this causes a lot of friction for developers who are trying to use these tools. And we found that this is actually a major barrier to these static analyzers being used more widely than they currently are, and more as widely as we might expect. So we sought out to try and solve this problem of static analyzer false positives by creating a machine learning based post filter that would classify Infer warnings as either valid or invalid after an analysis is already run on a particular software project. And so given a list of Infer warnings, including the file and line number in the source code where these warnings occur, we tried to classify each of these warnings to decide which ones we should keep and actually present to developers, and which ones should be filtered out and not presented to them. And we do this mainly using the source code of the repository or project itself, as well as some sort of debug and trace information that Infer itself reports for each of its warnings. So we took two different approaches to this. The first was a typical supervised learning approach, using a set of Infer warnings that had been hand labeled as to their validity, as to whether they're legitimate warnings or just false positives. And using this data set, we trained a transformer model, specifically a CodeBERT model or Roberta model. We took this model, pre-trained it originally on Java and C# source code just from GitHub, and then fine-tuned it just for binary classification on our hand-labeled list of Infer warnings. And then evaluated this on a test set of the same type of Infer warnings, just for different projects and from different files. Our other approach, sort of coming out of the supervised learning domain, was to use a model called GPT-C. This is essentially a GPT-2-based decoder model that was pre-trained on several different programming languages for the task of line completion. So given a snippet of code and perhaps an incomplete line at the end, this model was pre-trained to offer completion recommendations for the last line of code, which is incomplete. The way we use this model is to feed it in a snippet of code prior to where a warning is reported by Infer, and use the model's output recommendations as a signal of whether or not the warning is legitimate. So for example, if Infer reports a null dereference warning, we would give it the code prior to that warning and look at whether the model recommends some sort of null check. And the signal we would draw from that is that if the model recommends a null check is required, that may be a signal that the null dereference warning at the same line is indeed legitimate. And so because of the way we use this model, we use it in a zero-shot setting, which means that beyond its pre-training, we don't have to train this model at all on our labeled set of info warnings. So this doesn't need sort of a hand-curated set of warnings in order for this approach to work. Here's a summary of our results. We can see that both of our transformer approaches are able to increase precision beyond baseline infer by about 15 to 17% relative, and take somewhat of a similar reduction in recall as a result. However, we think this trade-off is actually favorable because from talking to developers in the field, we found that software developers tend to value precision over recall. And the reason for this is that if we present developers with a small set of very high confidence warnings, it's more likely that the developers will actually triage, address, and ultimately patch those warnings than if we try to find everything wrong with a software project all at once. Higher confidence, even in a smaller set, tends to be sort of more receptive to real world fixes. And I should mention these results are all on null dereferences. We also wanted to evaluate how well this post-filter approach scales to other types of warnings. So we wanted to investigate resource leaks. For this, we only used our GPTC approach simply because of the size of the data we had. Wasn't really amenable to further training. And what we found here is that GPTC, using a different set of sort of rules for the output checking, was able to increase precision slightly, but at the cost of a much larger reduction in recall. So the results here are certainly more modest than for null dereferences, but we take this as evidence that it's at least possible to use this sort of post-filter approach to reduce the false positive resource leaks with some further development. And we have a few different directions that we want to take this in the future. The first is to simply scale this approach to other types of warnings and other programming languages. We primarily focused on Java for the work that we've presented here. Another idea that we have is to try and use additional types of code context. Primarily in our work so far, we focused on extracting code context from the method where a warning is reported, or at most one other method somewhere in the code base. But we think that there's opportunities to improve this by using something like the retro framework to automatically retrieve additional context from across the code base to try and allow the model to better understand how the code base works as a whole, as opposed to just looking at a single snippet that may call many upstream methods. And then finally, of course, in addition to just detecting bugs, we also want to be able to fix them automatically and offer automatic patch generation based on the legitimate bugs that we find from some of these static analyzers. So these are some of the areas that we're sort of interested in moving forward, and the ways that we think we could potentially improve this sort of static analysis and machine learning complementary system to actually make it work in practice. And that's all I have for now. I don't know if we have more for the session. For your time. Sorry about that.
Well, thank you, Anand. So I think we have had the presentations from this session. I think we have one presenter missing for the paper. So unless we have a presenter for that paper, I think we can go ahead with the Q&A session. I think we already have a question for Jürgen from Diego. So Jürgen, do you want to answer that?
Sure, I can try. So thank you, Diego, for the question. We go a little more into this in the paper, but to bring up two, I think, interesting points that came up in the study. People really didn't like if we found explanations that constituted of many changes. So if we came up with the right explanation, meaning that if you change these 7 things in your commit, then your prediction may change, then that was super not actionable, because even if your commit is super large, it doesn't resemble the original commit as closely anymore, and frustrated with that solution. So just empirically looking at typical commit sizes that we had, I think like explanations up to 5 perturbations were okay. Usually if it was between 1 and 3, people were pretty happy. And maybe the other thing that I found was interesting, which had mixed responses, but the initial response that we got over the few interviews was that if the perturbation changed something in the context of the commit, as opposed to something that you actually changed in the commit, then people were unhappy, because then they told us, well, you're telling me I need to change something I can change, right? So they interestingly took it as some sort of bug repair replacement as opposed to an explanation, whereas other people understood it as what it was, namely it picked up on where the model was picking up its signal. So even if the perturbation that we introduced to find the explanation was not in the actionable part for you, it doesn't mean that it's not actually important to understand the model's prediction. But that was a sour point within the interviews, I would say. But yeah, great question, Diego. Thank you.
Well, thank you for the question. So Diego, did you came up to the stage, and then I think it's kind of moving around, but do you have a follow-up question? If not, move on to the next question.
No, I just should have expected just thank you for the answer. It was quite comprehensive answers. I'll check the paper for more information as well. Thank you.
Cool.
Sure.
Thank you.
The next question we have is for Anand. So Anand, would you mind coming up to the stage and answering Masood's question?
Sure, I'm just reading the question right now. Yeah, so with regard to the question of improving the rules of the static analyzer using the model's inferences, this is something that we've sort of considered at a high level, but haven't really explored sort of in any kind of concrete way. At face value, I guess the very short answer would be yes, we believe so. And what you would see in that sort of setting is less of what we did as a post filter that runs after the static analyzer. It would look more like a machine learning model that works in tandem with the static analyzer and sort of uses the model's inferences sort of at every stage of the analysis in order to make decisions about whether a warning exists or not, or whether code is buggy or not. So I certainly think it's possible to do that. The way that something like Infer works, for example, is it performs sort of a statement by statement analysis of how each line of code modifies memory state. And then at the end sort of examines these memory states in order to make decisions about whether some sort of erroneous condition happened. And that's where the sort of rules-based engine comes in. So you could certainly imagine something like, one of these transformer models that's been trained on the source code, acting on memory states in addition to the source code as well, and sort of having that be additional context in addition to just, here's the source code of the method, for example. And that could certainly make sense. I think that's something that, at least from, theoretical perspective would have a very strong sort of grounding. The other part of the question about, potential of analysis tools without analyzing dynamic behavior, I think there's sort of inherently a limitation when you try to consider the differences between static and dynamic analysis in the fact that static analyzers can't actually look at code runtimes. But from a practical perspective, there's a lot of value in being able to analyze source code without having to run it. Primarily when you envision like CI/CD environments or developers, wanting to know whether their code is buggy before it actually goes into production or before even they have to run tests on it. There's a lot of inherent value to that. This domain, so these techniques compare with traditional static analysis techniques. So I'm not sure I exactly understand the next question about machine learning and how it compares to static analysis techniques. Generally with static analyzers, you can kind of let them loose on a code base and they'll go and find bugs in source code in various different places. What we found from efforts to try and mirror that in machine learning, to try and just take a machine learning model and run it on an entire code base, is that they tend to also report false positives, but generally because these models don't localize bugs very well. So they can analyze sort of specific snippets of code very well, but when you let them loose on an entire code base, they tend to not be very effective, which is the reason why we sort of chose our post-filtering approach, to use the static analyzer first that can perform this localization quite well, and then try to use a machine learning filter on top so that we already have localized bits of code that we have to look at.
Thank you, Anand. I think the next question is for Jürgen.
Yes, Sebastian, thank you for the question. So the underlying models that we use to do this guess and check approach are transformer models. So they take as input whatever we train them on. In the cases that we looked at, the models that we were interested in, they mostly took commits. The test like the input to the model can be anything you want to train it on, right? The more complicated part of this is that even if it's like partial code or a commit, you do need to have some sort of parser or tokenizer that allows you to insert these masks for the pre-trained model in order to produce these perturbations that are natural. And the thing we're struggling with right now is, can we generalize this to many different downstream tasks that we work on? So there's no one tokenizer or one parser that works perfectly, obviously. But usually these pre-trained models come with their own tokenizer, and we're trying to figure out like a middle ground to make this as general as possible. But if you want to have perturbations only on some part of the input, let's say you only want to have perturbations in variable names and method invocations, then you will need to write your own parser to do that. Does that answer your question? I hope so.
Yeah, you
Okay.
have a follow-up.
Yes. Sorry, I was just following up on the chat to not mix up all the voices there. I'm happy to chat. I'm just staying in the chat to respect the protocol here.
Oh, sure. So the quick follow-up is, would your GitHub repo include the pre-trained? No, unfortunately, no. So the pre-trained models that we have are mostly internal. The GitHub repo will include all the code that introduces the search and the perturbations and stuff like that. In the future, I can probably provide like an open source version of like the end-to-end pipeline of having a pre-trained model, introducing these masks and so on. But happy to chat offline, Sebastian, if that helps.
Thanks, Jürgen. I think so. I have a quick question for Jeremy. So after that, I think we have one more question, each for Jürgen and Anand. So Jeremy, I was just wondering that Varclair, like what kind of tasks would benefit most from using this approach?
Yeah, this is actually a really good question. So while we were developing our decompiler renaming stuff, it becomes likely that you need some good metrics, and you need fast metrics that will, so you don't want to go and have to do a human study every single time you have a new technique, and then you have more machine learning that you need to do, and you tweak the model a little bit. So pretty much anything where you need to evaluate how similar two variables are, if they can be used for replacements. We have some examples in the paper, actually. One of them is, say, spell checking. Just doing that, it becomes harder and harder to evaluate spell checkers as you get better ones, as you do faster ones, and things like that. So yeah, tasks like that. And honestly, it's pretty wide open. Just like coming up with tasks is already a research project on its own. But yeah, pretty much anything where you would need a metric.
Yeah, well, thank you. Yeah, I was wondering because I think like if code summarization or generating comments, that kind of tasks would also probably could benefit from
Yep.
this. So
Yeah.
all right. Okay. Well, thank you. We have one more question for Anand from Jasmine.
Yeah, so this question's about vulnerability scanners. That's a great question, actually, because that's something that we're actually interested in, and we're trying to look into is how to take our approach specifically from bug detection as a whole to vulnerabilities in particular. I think since it's still something that we're very new to exploring, I think the most I can say about that at this stage is we found that vulnerabilities tend to be a lot more specific than just bugs in general. And what I mean by that is the sort of rules that and patterns that you see across various types of vulnerabilities tend to be focused sometimes to just a small number of tokens or only occur in a very small number of cases. They tend to be more rare than just sort of larger patterns of bugs that a lot of these bug detectors tend to find. And a lot of that is because the bug detectors tend to focus on very common types of software defects. So we're optimistic that this kind of approach could also be scaled out to vulnerabilities just because of how big of an impact they tend to have. But we expect that we're going to have to make some changes to it simply because of the sparsity of trying to hunt for vulnerabilities compared to sort of bugs at large. But that's a great question.
Thank you. I think, Jürgen, you have another question from Puyan. You're muted, Jürgen.
Yeah. Okay. Usually on Zoom I see it, but this time I didn't. Apologies. Thank you, Puyan. Those are pretty good questions. Well, we're not measuring plausibility in any way. The plausibility aspect, what we're doing is we're using the naturalness that comes with this masked language modeling as a proxy for plausibility. So on the one hand, we're sort of ensuring that the perturbed input is staying in distribution, which is good for the robustness of the explanation. But we don't have like another explicit way of assessing the overall plausibility. Like one example that does happen sometimes is we're replacing one method invocation with another that seems reasonable in the context, but for this particular object we're calling this on, the method doesn't exist, right? So that wouldn't be plausible, but it's plausible enough that the developer consuming that explanation understands, oh, okay, if I had used this more generic method and not this specific expensive method in the loop, it wouldn't have been a performance regression sort. So it's not 100% plausible sometimes, but it's plausible enough, and we accept that trade-off of using that method as opposed to going in and doing a bunch of program analysis to find like 100% plausible replacements. So we have to work with that trade-off.
Thanks, Jürgen. Related to this, I was wondering, do you foresee any way, for example, one way that I can think of is whether creating environment for evaluation, whether developer use these explanations or not, or they simply ignore it. Is this a kind of approach to evaluate this kind of methods for explanation in the code context?
I mean, honestly, I would love to do that. I think it's a question of the effort we can put into this. I'm still with Meta for a couple months, and so maybe we can make an effort to do like that, because it is in deployment. But currently, we're not doing these measurements beyond pinging people and asking them for their opinion. So there's no concerted effort right now, but I'd love to see it.
Yeah, and there are some metrics in NLP community like Blue Score, this kind of thing, where like it's used as a standard measure for evaluating how good they are. Are these applicable in code context or
I mean, we can use them. I'm not a big fan of them, honestly. I mean, I like all these NLP papers that report on these proxy metrics. But if you actually look at what the ground truth of explanation is, and then what they're comparing it to, I think we're comparing apples to oranges. So I do think that making a quantitative experiment out of how do people understand models through explanations is potentially misguided or dangerous. I feel like a more qualitative approach here will give us more insight whether these things work or not.
Right. Thanks. Yeah, I also agree that in this context, there's much more work to do, especially in the context of evaluation. But nice work. Thanks.
Thank you.
Thanks, Priyan, for the question, and thanks, Jürgen, for answering it. We have two more questions for Jeremy. I think Jürgen already answered Sebastian's follow-up question. So first question from Alexander to Jeremy is, what kind of situations are most difficult for Verclair to handle?
This is sort of a tough one. I might have to get back to you on this one. Yeah, I think I'll have to get back to you on that one. I'm not completely, I'm not actually sure. So I'll have to look into it. I'll see if the paper answers it. It might. But yeah, I honestly, off the top of my head, I don't know, which is probably the best answer I could give.
We do have another question from Masood, who asks, can you please comment on the suitability of non-SE pre-trained models for SE-specific tasks? Do we really need domain-specific models? As you might know, the same word could mean different things in SE and non-SE context.
Yeah, the answer is yes, we do need domain-specific models. Sorry, you're gonna have to excuse me. I had brain surgery recently, but when things like GPT came out, it's pretty obvious to go, oh, we just apply this to code. But you know, when you try that, all of these things start, all of these overloaded terms start having actual consequences. I'm trying to think off the top of my head, like things that have completely different meanings in the context of computer science than they do in the context of prose. But yeah, there are studies on this where just apply a natural language model to code and see if it works. And the answer is it doesn't really work well. So yeah, it's tough. It's similar to, I think it's similar to like applying an English language model to, I don't know, Dutch. Like a lot of the words are very similar, but it's just completely different, it turns out.
Agreed. I think like I saw Jeremy shaking his head when, we were talking about NL metrics to apply, and the question Priyan asked, Jürgen, I was like.
So there's actually literature on the unsuitability of BERT. I think it's an Ngram model or something like that, and it's just it doesn't capture some semantics that well. It's mostly a translation metric that somehow like misses semantics. It's pretty, yeah, it's unsuitable.
Agreed. So yeah, I think like we have covered all of the questions on the chat. So if not, please feel free to reach out to the authors if you have more questions, or chat in other rooms in ICSE. Last call. Any other question from the audience before we close the session? All right, great.